Welcome to Brain Vision.
In this problem, we're going to talk about the energy of a photon. So what we need to remember is that the energy of a photon is equal to hc over lambda, where lambda is the wavelength of a photon. This could also be written as h times f, where f is the frequency. H is the Planck's constant, and c is the speed of light. In our problem, we have the information that the dissociation energy for silver bromide is equal to, so the dissociation energy is 1 times 10 to the fifth joules per mole. And our goal in question A is to find how much energy, what is the energy of a photon necessary in order to dissociate one molecule of silver bromide. Now remember that 1 mole is equal to 6.02 times 10 to the 23 molecules. So the dissociation energy is actually 1 times 10 to the fifth joules per 6.02 times 10 to the 23 molecules. So this dissociation energy per molecule is 1.66 times 10 to the minus 19 joules. And if I divide it by 1.6 times 10 to the minus 19 joules, then, the joules per electron volt, then we obtain that this is equal to 1.04 electron volts per molecule. So this is the energy of a photon necessary in order to dissociate the silver bromide. In question B, we have to find what is the wavelength of this photon. Now remember that E is hc over lambda, so lambda is hc over E. This is 1240 electron volts nanometers divided by 1.04 electron volts. So this is 1192 nanometers. Then in question C, we have to find what is the frequency of this photon. Remember that the frequency times the wavelength is equal to the speed of light. So the frequency is the speed of light divided by the wavelength. The speed of light is 3 times 10 to the 8 meters per second. And the wavelength is 1.192 times 10 to the minus 6 meters. So the frequency is 2.52 times 10 to the 14th hertz. In question D, we have to calculate what is the energy of a photon that has a frequency of 100 megahertz. So remember that the energy is H times F. H is 4.14 times 10 to the minus 15 electron volts second times the frequency, that's 100, times 10 to the 6th hertz. So the energy is equal to 4.14 times 10 to the minus 7 electron volts. And in question E, we have to justify why the light coming from a firefly is able to dissociate a silver bromide molecule, while light with a frequency of 100 megahertz, isn't. Well, notice that the energy coming from a firefly, the energy of a photon coming from a firefly, is much greater than the energy coming from light that has a frequency of 100 megahertz, because the energy, as we calculated back in question D, is 1.14 times 10 to the minus 7 electron volts. And this is much smaller than the energy that we actually need in order to dissociate the molecule, which is 1.04 electron volts, as we calculated back in question A. And notice that the wavelength of light necessary to dissociate the silver bromide is at most 1192 nanometers, as we calculated in question B. And since the firefly emits in the visible spectrum, then the wavelength lambda lies between 400 nanometers and 700 nanometers. That's the visible spectrum, and that's more than enough in order to dissociate the silver bromide and expose the photographic film. So the answer is because the energy of the photon coming from the firefly is much greater than the energy coming from the radio station. Which concludes our exercise.